half-life is the time required for the amount of a sample to decrease by half. There are two types of half-life problems. The first type of problem we can just count because the amount of the sample is decreased by 1/2, so the numbers are easy to work with. For the second type of half-life problem, we need to calculate because the numbers are less easy to work with. And that's because the amount of the sample is not decreased by an even half-life. So let's look at the first example. How many half-lives go by when an isotope decreases from 2.4 molar to 0.3 molar concentration? If we start at 2.4, after the first half-life, the concentration will decrease to 1.2. After the second half-life, the concentration will decrease to 0.6. And after the third half-life, the concentration will decrease to 0.3. So the answer is that it takes 3 half-lives for the isotope to decrease to 0.3 molar concentration. For the next example, it says what percent of a sample remains after 4 half-lives and what percent was used up. If we start with 100% of the sample, after the first half-life, 50% will remain. After the second half-life, 25% will remain. After the third half-life, 12.5% will remain. And after the fourth half-life, 6.25% of the sample will remain. Now, if we subtract the amount of the sample that remains from the total that we started out with, then we should get the amount of the sample that was used up. For problems where the amount of the sample isn't decreased by an even half-life, we can calculate using the equations for first-order half-life and first-order rate law. We'll use the first-order half-life equation first to solve for k, and then once we have k, we can use the first-order rate law equation to solve for time. In the first-order half-life equation, T1/2 equals 0.693 over k, where T1/2 is the half-life and k is the rate constant. The question asks, what is the rate constant for the first-order reaction that has a half-life of 2.5 hours? Rearrange the equation to solve for k and plug in 2.5 hours. In the first-order integrated rate law equation, A sub 0 is the initial concentration, and A sub t is the concentration at time t. So how long would it take the sample in the previous problem to decay to 20% of its initial amount? If the initial concentration is at 100%, and then the sample decays to 20%, we're going to rearrange the equation to solve for time and plug in those initial and decayed concentrations, as well as the rate constant k that we previously calculated. The last thing that we need to know about half-lives is that they can change depending on the order of a reaction. So for a zero-order reaction, as the reaction proceeds, the half-life times decrease. For a first-order reaction, as the reaction proceeds, the half-life times remain constant. And for a second-order reaction, as the reaction proceeds, the half-life times increase. In the example, as the concentration decreases by half, the amount of time it takes for that half-life to occur decreases from 35 seconds to 15 seconds to 8 seconds. Since the half-life times decrease, the reaction is zero order.